Okay, so let's take a look at unit number 4, some review problems from unit number 4. This can be found on pages 267 to 269. So I'll get into the difficult questions right away. This would be an application type problem from 4.7. So it says question 14, a hot cup of coffee cools according to the equation, and this is the equation here. It says where T is the temperature in degrees Celsius and, big T is temperature in degrees Celsius, little t is the time in minutes as minutes pass. Which part of the equation indicates that this is an example of exponential decay? So let me just first talk about this equation. Now, again, I did a problem like this. If we did not have this plus 21 at the end, this is very easy to explain. You can see that the initial would have been 69 degrees, okay? And the temperature is being cut in half, and it's being cut in half every 30 minutes, okay, because it's T over 30, so it's per 30. So that 69 is being cut in half every 30 minutes. But just remember that there's this plus 21 at the end. So the initial, if this 21 is not there, the initial temperature would be 69, but since there's a plus 21 at the end, that shifts everything up by 21. So the initial is not just 69, it's 69 plus 21. That's the easiest way to come up with it. Also, the equation of the the equation of the horizontal asymptote, instead of it being 0 like it would be here, it is now 21. Okay, and it makes sense because the cup of hot liquid is getting closer and closer to room temperature, which would be 21 degrees Celsius. So let's just take a look at this. Which part of the equation indicates that this is an example of exponential decay? The fact that the base is equal to half, that is decay right away. Okay, because if the base is between 0 and 1, it's obviously decreasing, decay. If it's bigger than 1, then it's growth. B, what was the initial temperature of the coffee? Well, you can just plug in time equals 0 into this formula, or you could just remember that the initial is 69, but then plus 21. And so the initial temperature at time 0, that's going to give you 90 degrees Celsius, okay, when you plug in a 0 there. Okay? So let's take a look at question C. Use your knowledge of transformations to sketch a graph. So if it just wants a sketch, it does not require 5 points, it just wants a sketch. It's very easy to come up with a sketch and what we know about transformations and transformations of exponential functions. So we know what the starting temperature is, it's 90, so clearly here is 90, let's say, if this is 90. And we know the equation of the horizontal asymptote. The equation of the horizontal asymptote is always your C value, it's always this 21. So if I just put 21 down here, let's say, this is the horizontal asymptote, okay, otherwise known as the room temperature in this case. And so this is what this graph would look like. This graph would look like it starts at 90 and then it decreases and gets closer and closer to room temperature, to 21 degrees as time goes on. So let's look at question D. It says determine the temperature of the coffee to the nearest degree after 48 minutes. I'm not going to do that one for you. You can do this one on your own time, but basically all you're doing is plugging in at 48 in for little t, so you can do that on your own. Let's take a look at E though. Explain how the equation would change if the coffee cooled faster. Okay, so right now the formula is T of T is equal to 69 a half to the power of T over 30 plus 21. So if you take a look at this, again, the coffee is cooling, that 69 is being cut in half every 30 minutes. So every 30 minutes it's decreasing in temperature, this 69 is being cut in half. If you want it to cool faster, that means that the half-life of that 69, that half of that 69, has to happen quicker. The only way that happens quicker is if your t is over a number smaller than 30. So for instance, I could have t over 10. Maybe we're outside or something like that, or maybe you know, the coffee cools quicker. Well, this is happening every 10 minutes rather than every 30 minutes. Okay, this would cool faster. This number has to be a number smaller than 30 in order for this to cool faster, because that half of 69 is happening much quicker here than it is there. Okay, so that number that t is over, the denominator has to be less than 30 in order for it to cool faster. Explain how the graph would change if the coffee cooled faster. So how would this graph change? So if the graph changed, if it's cooling much faster, again, this wouldn't change. 90 would still be your starting temperature, okay? And 21 is still going to be your equation of the asymptote. It just has to be decreasing much quicker. This one decreases, you know, there you go. But this one has to decrease much quicker. So it may look something like that, much steeper. Okay, that's how it would change. And then it would get closer and closer to 21. But it got very close to 21 very quickly, where this one took more time to get closer to 21. So let's take a look at, and that would be more considered as a communication question. Let's take a look at 15. It says the value of a car after it was purchased depreciates according to this formula. Okay, where V at N is the car's value in the nth year since it was purchased. So N is years that pass since it was purchased, and V is the value. So let's take a look at A. What is the purchase price of the car? Well, your purchase price of the car is always your initial, which is that. $28,000 is the purchase price of the car. That's your A value out in front, your initial value. B, what is the annual rate of depreciation or of depreciation? Well, that's not your depreciation. Remember, how do you come up with the depreciation? Because this base is also your common ratio. Okay, so your common ratio is this. The car is only worth 87.5% of its previous year's worth. So how do you figure out how much it's depreciating by? Well, you just take 1 and subtract the common ratio, or the base, and you will get 0.125. Okay, so this is how much it depreciates by. It depreciates by 12.5% per year. Okay, since it's depreciating by 12.5% per year, your common ratio is this. It's only worth 87.5% of its original worth. And there's plenty of questions that I've done on this. Your C, what is the car's value at the end of 3 years? So car's value at the end of 3 years, you're just going to plug in a 3 in for your N, your total number of years. Just make sure when you do this that you do this to the power of 3 first, then multiply by 28,000. I'll let you finish that one on your own. D, what is the value at the end of 30 months? Now, 30 months, how do you convert that into years? 30 months, in order to convert months into years, you have to divide by 12. Okay, so 30 months divided by 12. So you can either leave this as, and this will give you how many years. So you're dividing this by 12. You can either leave that as a fraction, or you can, write it as a decimal. Either way is fine. So if you actually do 30 divided by 12, you're going to get 2.5 years. Okay? So just make sure that you're plugging in the correct years, because this N is in years. So you're going to plug in 2.5 into the years here. So this will be 0.875 to the power of 2.5. Again, do this to the power of 2.5 first, then multiply it by that number. E, how much value does the car lose in its first year? So how would you figure that out? Well, you'd have to figure out what the price of the car is initially and what the price of the car is at 1 year later. So I already know the price of the car initially. Okay, initially at time 0, the price of the car is $28,000. At 1 year though, I can figure out what the price of the car is. 1 year. Okay, so again, I'm going to do 0.875 to the power of 1 times 28,000. So if I do that, I'm going to end up with 24,500. So that's how much the car is worth after 1 year. This is how much the car was worth right at the beginning. So if it asks me how much value does the car lose, I just take the difference, 28,000, and I subtract 24,500. And if I do this, it's going to give me $3,500. Okay, so the car depreciated by $3,500. And then F, how much value does it lose in the 5th year? Well, if you just want to know during the 5th year how much it loses, what you'll have to do, just like this, how much value does it lose in the 1st year? If you want to know that, you have to know year 1 and year 0 and figure out the difference. If it wants to know the 5th year, you have to know the value of the car at year 5 and the value of the car at year 4. You have to figure out both. And then what you're going to do is you're going to take the value of the car of year 4 and subtract the value of the car of year 5. I'm not going to do that for you, but figure out V5, figure out V4, and then subtract. The difference is how much the car lost in value in the 5th year. So let's take a look at my last problem that I want to look at, which is 17. And question 17 says the population of a city is growing at an average rate of 3% per year. In 1990, the population was 45,000. Write an equation that models the growth of the city. Explain what each part represents. So again, this is what's happening. You have time and you have population as a function of time. Year 0, the initial, the population is 45,000. Now, mind you, year 0 is the year 1990. Okay? So time 0 is the year 1990. And it says it's growing by an average rate of 3%. So to grow by 3%, if you add 3% to 100, it's going to be 103% of the previous year. That's growth. The common ratio is bigger than 1. Coming up with a formula, it's growing per year. Okay, so population as a function of time is going to be equal to A, which is 45,000, times B, your common ratio is 1.03 to the power of time over 1. It's just time over 1 because, remember, it's growing per year. And then it asks us to use our equation to determine the population in the year 2007. So please don't plug in 2007 into that formula. 2007, as you can see, is 17 years later. So you're going to find the population at 17 years later, which is equal to 45,000 times 1.03 to the power of 17. So I'll let you figure that out on your own. And then it says, determine the year in which the population will have doubled. So if you know that the population is equal to this, 45,000, 1.03 to the power of t, you want to know when the population would double. You're trying to find the time where the population is double of this. Double of this is 90,000. So I'm going to plug in 90,000 into this formula and solve for t. I'm going to divide both sides by 45,000. And that will leave me with 1.03 to the power of t is equal to that divided by that is 2. How do I solve this? I use logs. I'm going to do log of 2 is equal to log of 1.03 to the power of t. Remember, you're using logs because you're trying to solve for the exponent. So this is log of 2 is equal to t log of 1.03. Divide both sides by log of 1.03. And I'm going to get t is equal to log of 2 divided by log of 1.03. Okay, and I'll let you finish that one on your own.